According to Newton's third law of motion, for every force acting on a body, there is an equal and opposite reaction. The jet engine works on the same principle. A fluid, a gas or a liquid, is forced in one direction, which creates an equal reaction in the opposite direction, which moves the engine and hence the aircraft. An example of jet propulsion is seen in garden sprinklers. Jets of water are forced through the nozzles and as a result rotate the sprinkler. The simplest example of a gas turbine engine is the turbojet. It's essentially a tube open at both ends with air passing through it continuously. Air enters at the inlet, gets compressed by passing through a series of fans, gets mixed with fuel and heated by the combustor, then expands in the turbine, and finally the combustion gases are released through a nozzle to provide thrust. The design requirement and the operating conditions that the jet engine impose create great challenges for the materials that the different parts are made of. The compressor needs to squeeze air into the engine at a rate of 1 tonne per second, which is 200,000 horsepower, which is equivalent to the power of 250 Formula 1 cars. As the turbine rotates, the force of the passing air drives the compressor to suck in more air. Each blade is pulled by a centrifugal force of 18 tonnes, which is the equivalent to the weight of 2.5 elephants. And yes, we know centrifugal force is not a real force. The air leaves the combustor at 1600 degrees C, whereas the turbine blade material melts at 1200 degrees C. So how does the turbine blade survive under these conditions? As a result of the harsh conditions inside of a jet engine, a turbine blade undergoes a creep deformation. This is the tendency of a solid to deform permanently under high temperatures and constant mechanical stress. See the light alloys video for more information. There are 3 stages of creep. Primary creep is characterised by atoms slipping past each other, causing irregular lines in the lattice called dislocations. Under the applied load, dislocations can easily move by different mechanisms. One such mechanism is dislocation slide, which is also known as glide or slip. However, as the number of dislocations increases, they start to accumulate as certain defects within the material, and it becomes more and more difficult for new dislocations to form. The balance between these two processes is achieved in a steady state stage of creep, which also takes the longest. The final stage is tertiary creep, which is the fastest and leads to the failure of the material. A component spends most of its lifetime under steady stage creep, so minimising creep in this period is the most important. So going back to our turbine blade, creep causes the blade to elongate, and therefore after a certain period of time, the blade strikes the engine casing, which is, well, bad, as you can imagine. To avoid that, turbine blades are made of creep-resistant nickel-based superalloys. What drives creep is the motion of these pesky little dislocations, so we need to slow down dislocation movement if we want to reduce creep. In the light alloys video, we saw examples of hexagonal close-packed and body-centered cubic crystal structures. Nickel-based superalloys are based on nickel with additions of aluminium and/or titanium up to 10 atomic percent. The gamma phase has a face-centered cubic structure where the nickel atoms are positioned at the corners and the faces of a cube, and the aluminium and titanium atoms are spaced within them. In contrast, the gamma prime phase is an intermetallic compound where the aluminium and titanium atoms are positioned at the corner of the cube and the nickel atoms are positioned at the face centres. As a result, the alloy forms a very stable structure where the sides of the cuboids match each other, even at high temperatures. But at the same time, the gamma phase acts as an obstacle for dislocation motion. This is because the gamma prime phase forms an ordered structure of atoms of different sizes compared to the alloying elements within the gamma phase. So we can slow down dislocations by having 2 cubic arrangements of the atoms, but this only works within a single grain. Most crystalline materials consist of millions of grains, separated by grain boundaries. Within a single grain, atoms are arranged systematically, and grain boundaries separate neighbouring crystals, with different orientations relative to one another. As engineers started to understand creep better, they found that having grain boundaries in the direction of the load increases creep. This happens because creep occurs by the diffusion of atoms through the material between areas of different stress. Grain boundaries are regions where many defects start, which makes diffusions of atoms easier, so individual grains are less susceptible to creep than many fine grains. This is the idea that drove the historic development of turbine blades. In the early stages of the 1960s, blades contained grains of similar sizes. Then the next generation was formed from long grains solidified in the direction of the applied load. Now modern turbine blades are grown out of single crystals. In addition, small channels are engineered inside each blade for cold air to pass through, and sometimes they are coated with an insulating ceramic layer. This helps to keep the temperature of the blade nice and relatively frosty below 1000 degrees C, even when the turbine entry is 1600 degrees C, thus enabling the turbine blade to survive another day. Thank you for watching this Metallurgy Minutes video brought to you by the Advanced Metallic Systems Doctoral Training Centre based at Manchester and Sheffield Universities, UK. Please check out our other videos and give us a like on Facebook.